All right. Interesting. Hello and welcome everyone to Celestial Theodolite update number 20. Last week we were dabbling a little bit in the math of the spreadsheet, going over everything. There was not yet a fully prepared guide for everything as there should have been, but that has been taken care of. I got a nice rough draft of everything written out, so we're going to go over that. And hush your hot mic in a little bit. Thank you, sir. All right. So if you guys want the links to everything, I'll put those in the chat now. So Theo update number 20. Link in the chat. So you guys can use that as a resource. Now, included in this is also definitions and an introduction. Everything else will be filled out as I continue. It's a long process to go through this, but when all this is done, you'll be able to reference this as a complete guide for everything for the related to the celestial theodolite, an introduction to the subject, what it is, the null hypothesis, how that works. And then more importantly, you'll be able to get a notation index for the spreadsheet. So that way, when you look at what I'm looking at and talking about what I'm talking about, you can understand what all these words mean, because without understanding the notation, you would have no hope of, articulating what any of this represents. So to kind of help facilitate the transition of learning the two, I came up with this. And then there's also definitions here. So when you go through and start reading through these, like the celestial refraction section, which we went over last week, which actually it'll be updated here. And then we'll do an update probably next week on the celestial refraction stuff. But you can go here, reference this, and then as you come across words and stuff you don't know, you can click on the definitions. It'll take you over here, tell you exactly what is being referenced there. Okay, so to go over the spreadsheet, we're going to understand everything that is on it here, and then we'll by the end of it, we'll understand what everything is representing. Okay, so to start us off nice and easy, we got occlusion timings and dates. These are the times and dates that the occlusion was recorded at. It's very important information. And it's useful to find your UTC time. It'll make it easier for everyone else that's dealing with the data and trying to, reproduce where the star was in stellarium, etc. It's much easier to deal with that. So make sure you get your UTC when you record your data for ease of convenience. Now, celestial navigation is built on the principle of time equaling angle. So we can use this, we're all familiar with the process and how we're externally testing an internally consistent system. But the basic premise here is time equals angle. So the occlusion time will correspond to an angle at which the star was. So suppose we have a mountain peak to start us off, and we want to know what the relative angle is between, what the physical elevation is of that angle of that mountain based on our location. So we would have the H peak here. This represents the height of the peak. Height observer is your relative elevation above sea level. All of these are above sea level. That difference gives us the delta H peak. This is going to be the relevant information for the next part of the analysis in the spreadsheet as it moves forward. This is the relative geometric angle of the occluding peak if there's no drop over distance. And then next up we have theta star peak true, theta star peak apparent, all the way to observer true, observer apparent. All of these are referencing where the true position or the apparent position of the star is with respect to the peak or the observer. So when we're doing the analysis, these will be the included terms to know what the analysis is relevant to, either the peak or the observer. So to kind of go over that, we have the position of the star at the time of the occlusion with respect to the peak rather than the observer's location. The movement of this position is modeled by 15 degrees per hour. It's unaffected by astronomical and terrestrial refraction. The true position is the reference position for how much astronomical refraction is to be applied at any particular angle, and the sky to maintain that 15 degree per hour relationship, which is referencing its Aries ground position. The theta star peak is the apparent position, that's just the refracted position that we're all familiar with. Now they're saying that the angular separation between the true position and the apparent is due to astronomical conditions, and that is and that amount of difference is their astronomical correction, otherwise known as astronomical refraction. Star observer true. This is where the true position of the star is with respect to the observer location. Following all the same rules that we just went over for the peak, just apply that to the observer location. And same with the apparent as well. That's just the amount of refraction between the true and apparent position for the observer. And in these cases, they come out to be the same exact amount. So like when we go to the peak, there's not like a different amount or anything like that. Standard astronomical refraction is in here, but we went over last week as to why we're not going to include that in the analysis. It's improper to mix those two. And we got M bar here. That's just a calculator for what number to put into stellarium to get the proper amount of claimed astronomical refraction at the time. So you want to get your M bar in there, and that'll adjust based on the relative altitudes and stuff that you put in. So the standard refraction, of course, that was calculated by the distance over 150,000 meters, which converts 7/6R into degrees per meter. Yeah. Oh, I think that might actually be correct then. I might have misspoke then. I need to put a comma in there to make it easier to read for me. Yes. Yes, thank you, sir. All right, then radius of Earth, that's just your radius of Earth in meters. So 6,730,000 or something like that comes out to. And then we have angle adjuster, which used to correct offset. So if you want to do testing or whatever, you can enter an angle adjusting thing. And so now that we've gone over this section of the spreadsheet here, we're going to cover the calculations that we're going to do based off of the information that's on this side of this. So we have distances, we have our delta H for the peak, we have our angles for stars. And from that, we're going to start to do some trig functions, and we're going to go over what those trig functions are now so we can give a nice, easy explanation for how they work. So to start off with, we come up with the rise over run for the peak. This would be what the elevation or the angle that would be produced if there's no drop over distance to the peak, because in the globe Earth model, they would say that the physical peak is, tilted away from us. So that's creating based on drop over distance. So that's creating a lower physical elevation for the peak relative to us. So we're comparing the difference between the two models here based off of what the physical geometry would predict, because that's what does the occluding in the occlusion process. So we start off with the theta geometric flat Earth peak predicted angle. So this gives us the rise over run to the peak. And this is just arctan rise over run to give us the peak angle. And that just involves the this relative delta, this delta H here, and the distance. And then to continue on, we have the delta theta star peak flat Earth true intersection. So this is the difference between where we predicted with rise over run, where the star would intersect with the peak. So this angle right here, this 231, and then where the star actually was at when it was occluded. So we have this referenced over here. Oops, let me put this on Pike's Peak. So when we go to Pike's Peak, we see that the star at the peak was at 233 instead of our predicted 231. So that gives us our difference there of 2 arc minutes. So that's what that's in reference to. And we can also use the same trig function because we have a distance and an elevation, or I'm sorry, yeah, distance and an angle. We can convert that into what the rise would be. So we can also see what that would represent in meters to kind of look at it that way. So if you could kind of like bring it down to scale, what it would look, what it would look like is that the true position of the star was off of the peak by 2 arc minutes, which created a 30-meter angular separation, or a 30-meter separation, if you were to convert that angular amount into a meter separation. Because it's easier for me to think about this in that way. So a lot of these will be converted. You'll see the units converted into meters, so you can kind of do like an elevation comparison. All right, so moving on now, we have the theta h FE peak. So this is deriving the elevation of the peak based on the occlusion time and the distance. So here we're independently deriving a distance based off of one of the other known variables and the occlusion time, whatever the occlusion angle happens to be. And what we get with that, we will do the double delta H of the peak, and that is the amount that we derived minus the true amount, and that tells us how much we were off by. So when we do the trig function for that, we get this, we're off by 30 meters. We're above the peak by 30 meters, essentially. And we do the same thing for the distance function. So because we know one of the other variables, we know the occlusion timing, and we know the true elevation, we know the delta H. So now we can derive the distance now. So when we do that, we get this number over here, applying the same kind of trig function that we did to get the elevation, but just using the opposite of the other known variable that we already knew. And that gives us the flat earth distance derived. And then we just kind of compare. So in this instance, our true distance was 50,550 meters away. We derived a distance of 49,884. So we were 666 off. So with that, we see that we're pretty much spot on for our location there. Now we go over how we're doing the globe. So we got some notation here. So we got some theta geo terrestrial drop 180, theta geo globe peak predicted, delta theta star peak true, or globe earth true intersected. So we're just kind of replicating the same situation here. But what we're doing here is we're using the equation 180 times the distance over 2 pi r to get how much angular drop and or a drop over distance in meters, because you can convert it to meters in that. So how much drop over distance there is for that. Then we could subtract that from the elevation of the mountain peak, because we're gonna go. So subtracting 8 minutes of angle from the peak, from what the flat earth would predict, is the equivalent of saying that the peak is lower by 200 meters in elevation because the earth is a globe. So if you were to get out your terrestrial theodolite and measure the peak, the angle would be about 219, because that wouldn't have to include terrestrial refraction, but it would be based on adding refraction of 2 arc minutes to a raw angle of 217, because the physical elevation of the mountain, they're saying, is missing 200 meters. And that's not, their assertion is that that's a physical effect of the earth, of the terrestrial globe. We're saying it's an optical effect, and it's not physical. But either way, we agree on the visual angle to the peak from that distance. Whether or not the mountain is actually missing the 200 meters is what's in contention, and that's what the celestial theodolite can help us with, because the star's occlusion angle will correspond to an angle that's either closer to ours or closer to theirs. And then when we backwards derive, I say backwards, but when we just do the trig functions to derive the other variables, the distance and elevations, we get closer approximations than what they do. Now, an important distinction here that's kind of been lost is that we've been analyzing and giving the benefit of the doubt for the apparent position of the peak, and we haven't been doing the actual comparison for the geometry of the globe using the true position for the analysis, which, basically because none of them would agree to that, because then they have no possible way for the fair comparison. But we'll include the numbers here anyway, so we can see the representation when we actually apply true position of the peak to peak for globe and flat earth, rather than just doing it for our position and then accepting the true position refracted. The refracted position from the observer location for the analysis, because we're interested in the geometric intersection between a light source and a terrestrial feature that has a known elevation. So that is the actual premise of this and purpose. because a refracted position can't occlude something. So anyway, we'll get further into that as we continue, but all of that will be noted down here, and the lighter pink by the deltas down here. So as we go through those, we'll get on to that. Okay. All right, so now that we've went over what the what all these represent here, we'll go ahead and go over the formula. So we got 180 times the distance over 2 pi r. So this is going to tell us how much drop over distance there is. That's going to tell us the vertical drop of an arc length. So if you were to do 360 times the distance to use a central angle to derive an arc length, this would be the amount of drop over. This would be how you determine the drop over distance of said arc length. And similarly, if you were to derive the distance using a chord, this would be the drop over distance for that chord. I think Shane has the numbers for using an arc length versus a chord over these distances, where the distance is only 50 kilometers. 100. I think the longest one was 130 kilometers. So like over these distances, the difference between the arc length and a chord is 14 centimeters at the case of Pike's Peak. So we're not, it's not going to produce any noticeable difference. So we just treat that arc length as the chord approximation. All right, so to kind of walk through what we're going to do with that, we just subtract that now from the flat earth angle, because that's going to give us the drop over distance for that, and that's how we got that. So the theta globe peak predicted now is their geometric intersection point. So when we look at this, we have we just subtracted the terrestrial drop over distance of their arc length or chord from the no rise over run, and we got 217 there. Now, when we compare the true position of the star at the observer location to their 217 peak, we get an 11 arc second difference there. We had a 2 arc second difference before the occlusion happened. All right. Then let's see. Continue down. Now, in the same respect, how we derived elevations and distances for flat Earth based off of the occlusion timing, we can do the same thing to see if we can get back to the physical elevation predicted by the globe for the peak. So what we have here is the globe geometric peak minus the terrestrial drop. That gives us the actual prediction for the globe peak. Now for the for how we derive that, oops, 1 second. So doing the same function that we did earlier, which was just the tangent of the distance, or the tangent of the occlusion angle times the distance, giving us the giving us a distance produced out of that, or that would be for the elevation. That gives us the elevation predicted, so we can compare and contrast based off of the occlusion timings, what distances and elevations they derive, and they should be closer to what they predict. And what we find for in the instance of Pike's Peak here, they derive an elevation that of they derive an elevation that is 2,026 meters. Sorry, I just adjusted everything recently, so I kind of have it memorized in different positions. So they predicted an elevation out of that, based on their occlusion difference, of 2,026 meters. So they're basically their drop over distance. They're bound to their drop over distance. So they're 201 meters off. Now, when they derive distance to that, they end up being 5,000 meters off. They overshoot it. And this trend kind of continues for all the measurements we've been over before. So I'll skip going over like other peaks specifically, because we're just going over what the math is for each one of these. but we're just doing a fair comparison to what we're doing for the flat Earth just based on the occlusion angle. So it's like, what was the occlusion angle? Okay, well, they're predicted. So for their instance, we're using their geometrically predicted occlusion angle. And for the comparison, that's why they're off by that. So if we were to circularly derive it using Earth's radius, then they would never be off on the distance because it would always be circularly bound to the radius, and it wouldn't be independently telling us anything. So we bind it to their geometric prediction, and there should be 200 meters missing of it, so they should correctly predict this elevation if you were to subtract that from the amount of drop over distance from our prediction. So this is the difference here. Okay. All right, now we get into the geocelestial drop 360. So what is this? What is this doing? This is telling us how much the star had to rotate over that distance to be at the angle that it is as it traversed the sky. So as it traversed that 50,000 meters here, this is the amount of angular drop in the sky that had to occur. This is called a central angle, and we'll get into some diagrams as we go forward, but it's extremely important because this geometry represented here is true whether the Earth is flat or a globe, because we're representing it of a hemisphere, where our argument is that it's a hemisphere of vision. The globe would argue that the terrestrial features create this. But either way you slice it, this is how you describe the movement of the star overhead relative to what you see. Okay, so this is the angular equivalent of binding 15 degrees per hour and 60 nautical miles per degree. By binding the radius to the distance in this equation, there's an inherent conversion to nautical miles to meters in the form of 1-to-1 arc minutes, or in the form of 1-to-1, which is arc minutes to nautical miles. And what you could do is you could subtract the difference between the true position at the peak and the true position at the observer. It comes out to be 45, which when you convert that from decimal degrees to degrees, minutes, seconds, it's 27 arc minutes. So that is how far that is the rotation of the star in the sky over that arc length. Okay, so in other words, when we look at this diagram here, we have Nicki Minaj. We have a star at her zenith. In order for the star to get to the mountain peak, it has to move 90 degrees in angle. Now, terrestrially, though, she has to look down at 45, which she from your plane of observation, you only perceive 45 degrees of this angle, whereas the star had to basically go from her zenith all the way down, had to traverse 80, 89 degree, or like 89 degrees, or like 88 degrees, close to 88 degrees, 87 degrees to get down to the horizon to be at 2 degrees and 31 arc minutes. So this is what that equation represents. And 180 times that arc length is the vertical drop over distance of that. So that's how that relates with the pink line. So the drop over distance would be half of the arc length of the sky. Very interesting relationship. All right, and we have some other diagrams that are more technically inclined to illustrate the same relationship, that the central angle here that the star has to traverse across the sky relative to what the observer sees, half of that would have to be, like, let's say hypothetically we live on a flat Earth, you would have to, and you were say that we lived on a globe, but fake it. You would have to, your astronomical refraction would have to be half of the drop over, it would have to be half of your terrestrial drop. It would have to be 180 times the distance of your central angle. And when we go through the analysis, which I'm not sure, we'll see where we're at on time. We'll go through a couple after we yeah, we're good on time. We'll go through a couple after we continue on. But this is an extremely important factor because essentially, let's say hypothetically the Earth's a ball, but you would be canceling out all of the drop over distance between you and whatever object is between you and the star every time, or tripling or even double or triple compensating for it essentially, and just being like, well, it's definitely a globe, but it just looks extra flat because of these refraction conditions, and it's all related to that in the math. So you can see like why that geometrically works out as to it being half the angle. All right. So hopefully that helps explain the relationship there of what we're representing, to put some visuals to the math there, because the math gets a little abstract. And if you're not familiar with anything, like I'm just kind of learning all this for the first time myself. So this is all recent. So these diagrams and having it really explain the significance of the equation that's being put forward, because it doesn't, like this is the movement of the star in the sky to produce what you would see when you look 45 degrees of that angle terrestrially, as it just traversed the distance on the ground essentially. So that's a huge concept to understand, because whether the Earth's flat or a globe, that's true, and that's an important concept to understand. Okay. Let's see here. So I think I covered that pretty good. There's some additional text here that give clarification, but I think I covered that pretty good. So I'm not going to add more to it and overdo it. So by coming up with that geometric celestial drop over distance there, we can also do a comparison to see if the star is at where it's supposed to be, to follow the 15 degrees per hour and 69 nautical miles per degree. And for me, I was previously doing it incorrectly, but when you subtract it from the star angle, there's no offset, so everything appears to be on the up and up on that now. And this is more of a continuity check, just to make sure that there's never an actual error that's independent of my circular mistake. Okay. Because I was previously relating this offset right here, like our intersection difference, to the globe intersection difference, but they in fact have a different intersection difference. It's 11 here, but anyway, I was doing it circularly, so it was coming out to be the same, and that led me down a very long road. But we're back on the other side. Okay. All right, so to continue out here, we then derive distances and elevations based off of the true position at the time of occlusion for the observer. So what it would be relative to their derived peak. And when the figures that we get for that, they derive an elevation of a peak that has 1,856 meters, so they're off by 317. Then for the distance, they're off by 10,000. So they derive a distance of 60,000. So their triangle gets all screwed up there, whereas our triangle is more or less preserved based off of the occlusion timing going true to true. And then to even get kind of like a resemblance of being close, they have, we do true to their geometric peak, what they predict. And sometimes it works out a little better for them, but it's not, they're still off by 5,000 meters there. All right, now the last part, since we spoke, there's a more coherent analysis, not just going over the what we did, like in terms of like mechanisms of refraction and how terrestrial and astronomical interplay or don't interplay. We now have a way to look at how the amount of astronomical refraction affected the measurement. So to go over that, we have theta, astronomical refraction, stellarium. So this is not quite sure what equation they use, but it seems very similar to the G.G. Bennett formula. But what we do is we just subtract the difference for the true position from the apparent, and that gives us how much refraction they say is there at the time. So we use that as our value for everything. And because we have a distance in an angle relationship, we can derive liftover distance instead of dropover distance, how we were doing it with the tangent function. We can do the same thing to derive astronomical lift, you could call it. So you could do liftover distance, and we could subtract that liftover distance from the dropover distance to see what that comes out to be. And in this case, if they say that at Pike's Peak, they say that at Mike's house, if you're observing that star, there's 12 minutes of astronomical refraction, and relative to that peak distance, that would give 186 meters of lift. And there's supposed to be 201 meters of drop. So this creates a 14-meter undercompensation. So here they were unable to geometrically compensate for the amount of curvature that was expected. They were off by 14. They were geometrically off by 14 meters on their astronomical correction. And which is a huge failure for them. And that's like kind of the importance of all this, because even when they, when we go through the other measurements and we see that they're double and triple compensating for their curvature, it's like there's instances where it completely fails. So then we have so we call that the delta geometric terrestrial drop comp. So that's just subtracting the amount of actual drop over distance over their liftover distance. And then we have astro refraction compensation. This gives us this is just dividing the amount of refraction by the drop over distance. And that ratio is a percent, so 93%. So they undercompensated. And we'll see how that changes. This is one of the few times we're seeing an undercomp. And then theta astro refraction comp effective, that is how much astronomical refraction allowed that star to overcome that peak. So it was able to exceed the peak by 1 arc minute there. So it was like basically how much it helped it out, All right. And then like in some cases where it didn't work out. But that's pretty much the gist of it there. Nothing too crazy. Everything I went over was just some subtraction formulas and division to get a ratio, and then more subtraction. So when we go over and look at what this looks like now, when we put some figures to it, let me zoom in a little bit, see if that helps. We've been looking at Pike's Peak here for a minute. We'll just do a quick recap. They overcompensated, or they undercompensated by 14 meters, but they, essentially that would be like enough refraction to make the Earth appear to be flat and not a globe, would be their position normally. But now because we have this peak intersection situation, the position that the star had to get 12 arc minutes below the peak, so to speak, before it was occluded for the observer is untenable, because it actually occluded when there was only 2 arc minutes of separation between the peak and the star. So when it traversed that distance to complete its 90-degree rotation from zenith to horizon, that's when it got intersected. Not when it was at the angle that would be predicted out for, Nicki Minaj looking at it. She didn't occlude the star. The peak did. So as it's traversing that 27 arc minute drop from observer to peak, it got occluded earlier, it got occluded earlier than what would be predicted if it had to get lower, because there was an actual 200 meters of missing elevation at the end of that at the end of that 27 arc minute traversing of the sky. So we intercepted that peak, or we intercepted that star 2 degrees, 31 arc minutes in the sky, and it should have been 2 degrees, 27 if it's a globe. And then suppose there was no peak there, right? Suppose we were just looking at the raw star and we were like, hey, that star, how much refraction is there? Well, they would go, oh, well, relative to our distance, its true position is 206, and there's 12 arc minutes difference between the true, the true and apparent there. So it's at 218. So without, and you would just assume that that angle that it's at, that visual angle, you would just assume that, oh yeah, okay, there must be 12 arc minutes of refraction there between us. But there doesn't really appear to be, though. It appears to be much lower. And that would be represented by the difference in this intersection angle. And as we go forward for other peaks, now I don't even know if that's like the actual amount of astronomical refraction, because I like last week, I heavily alluded to that, but the difference in Mount Rosa is only 30 arc seconds. That's essentially saying that there's no refraction there. And that does, so I don't know if that's an artifact of like actual refraction differences or what, but this is the intersection difference that we're looking at. And it's always closer to intersecting with the peak's true position as if there's no drop over distance, is what ends up happening. So when we look at the refraction analysis for this, now that we've been over the formula a little bit, we see that there's 101 meters of drop over distance. So that comes out to 9 arc minutes. So we subtract 9 arc minutes from the rise over run to the peak, which gave us 1 degree and 16 arc minutes. And with that amount of drop, when we start, we're gonna look at how much astronomical refraction they're saying had to, how that would apply over the measurement for that drop over distance that created that 1 degree 6 arc minute physical elevation for the peak. Well, when the they end up compensating for it with 17 arc minutes of lift. So they have 9 minutes of drop, 7 minutes of lift, and that comes out to being 180 meters of lift. So 180 meters minus 100 meters of drop, they're in excess of 80 meters. They overcompensated by 80 meters of terrestrial drop over distance that they would claim exist. This is a 178% overcompensation for the drop over distance here. And the amount that they added or claim to exist there put them at 2 arc minutes over the peak at the time of occlusion. And then we'll do, let's see, we'll do North Peak. So here we have another instance, that rare case where they undercomped. So this was the longest distance here. This was 130 kilometers. And the drop over distance for this is 1,340 meters. The refraction amount that they say existed is 23 arc minutes. When we do the trig functions for all of that relative to that distance and elevation, we come up with a lift of 886 meters. So they were unable to compensate by 455 meters. And the ratio of that comes out to be 66% of refraction to the drop over distance in terms of compensation. And they suffered complete geometric failure there. Another instance of that where they were unable to predict it. Now, here we were off on 13 minutes of separation between the peak's true position, because we predicted 44 arc minutes for the physical elevation of the peak, and the true position of the star with respect to the peak turned out to be 58 arc minutes. So 13 arc minutes of separation for us, and for what the globe predicted for the physical elevation of the peak and their true position, there's a 21 arc minute difference. And yeah. So anyway, you can see how that separation affects the distances and elevations that we derive over there, but it's not. So this refraction separation difference, though, isn't quite what they suggested is there. And then when we look at, let's see, we can do the blend mountain with 3 cap with the 3 cap star. So here for the drop over distance, or I'm sorry, for the physical elevation, it's 52 meters. The actual intersection difference was 14. And for what the globe predicts for geometrically, they predicted at an angle of 41. And let's see here. Their drop over their celestial drop was 22. Their astronomical refraction at this location was 26 arc minutes, which gives them 313 meters of lift to compensate for their 131 meters of drop over distance of that. And let's see here. When we derive elevations and distances based off of occlusion time with respect to the peak, we see that the peak's true position was at 38 arc minutes at the time of occlusion. And that gives, let's see, the globe ended up being off by their drop over distance, of course. So they got an elevation of 498, whereas we predicted or derived for 457, giving a difference of 172. So they're pretty close in difference there. That's only like a 30-meter difference because the drop over distance worked out to be what the angular separation amount caused us to be off by as well. So we're very close in elevation there, but then distance wise, we're off by 5,000 and the globe got 10,000 on that one. So it was closer, but that's in reference to, let's see that, what's it called? The angular, like the separation between the offset there. There we go. Where is it? Hang on. The offset. Oh, there it is. There's their offset. Sorry. I should. I don't want to make it bold because then they're all 3 bold. But anyway, the thing I was looking at was right here. So their intersection is off by 25 arc minutes, but you would have to basically completely compensated by astronomical refraction to create the to put the apparent position to what the globe geometrically predicted there for that. And so there exists a specific location of the ratio. That's what we were going over last week, where there exists a ratio of where the refraction compensation for the drop over distance will equal out. And that's exactly what we're looking at there. So is that enough to refute the null hypothesis? I don't think so. It would be, that just means that there exists a location per measure, at as a ratio of distance and elevation away from something to facilitate that amount of astronomical refraction. And the key factor in that turned out to be being at sea level, because that's where you would get the most amount of it. And so that's what we were going over last week. But this is how you understand and get to the point where you can kind of see what that means and how that compensation factor facilitated that entirely to work out mathematically, even though when we follow the arc of the star to its occlusion timing, it was 14 arc minutes off of the rise over run to the star, whereas they're 25 arc minutes deep and not, and requiring the apparent position mixture to explain it. And our position is that we're interested in the true intersection differences to determine the geometry of the Earth. So this, basically proved our point that the globe exists as refraction corrections. In every single case, except for a few where the globe wasn't able to overcompensate. They overcompensate by, even in this instance where there would be 130 meters of drop, they got 330 meters of lift. So that is, hopefully this helps with the spreadsheet. And now that there's a guide available, it can be read and interpreted. So if anyone goes over this, has some feedback, please hit me up and how I can improve it. And I think that's everything I wanted to cover. Mike, did you want to add anything on the 360 times the drop or anything? Yeah. See, I did not see it that way. And it took some assistance to get me there. Someone who was real familiar with the triangle situation. But yeah, once you once you get that, it's like that's hugely significant because like you said, that's true on either model because that's just the movement of the star over that distance as you perceived looking down at 45 degrees relative to the starting zenith of it. Like that's huge. Oh, can you walk me through the formula to put in to do that real quick? I think we were going over that before we transitioned over here. Go ahead. Oh shoot. Okay. Thank you, sir. Let's see. Do you phone? Testing 1 2. Say something.
You want
I
me
know
to say
why.
something?
Okay. No,
Yeah.
Shane, you don't know why. Don't, you don't know anything, Shane. You're stupid. Okay. So Mike
Should I try
said,
again?
no, I got you. I'll do a quick recap. So Mike said that he thoroughly enjoyed the Nicki Minaj diagrams that explained the 360 times the drop over distance and understanding that portion of it as a central angle sweep of the sky, meaning that how much the star had to move across the sky to get to the position that you see it at. Whereas, as it traversed that terrestrial distance relative to the observer's looking at it from a 45-degree angle. So it's always that half relationship of it is you have to pick me up from there, Mike. That's where I lost it.
I thought you were doing great. But The main point here, I think, is what I personally found is the important thing to focus on is that negative 30, and there's a corresponding negative 30. So I think it should probably be called the delta theta star comma globe comma GE comma true intersection. So I do see that. Oh no, not I almost see that down here. Um, so that one's like the drop minus um, the delta. But anyway,
Yeah,
so it's the delta. It's the difference in height predicted versus measured that's important, and it's the same. That height difference, the delta height error, is the same whether you measure it on the peak or from the observer's location. They're both off by exactly that 30 meters. And they're both measuring 30 meters high, so it's a negative 30 offset.
can you show me
Um,
what formula to add to show that? What cells do I
so
need to
that
hit
would
to get that?
be the distance time the tangent of um, I'm looking for the angle that the globe Earth would observe. Oh, 813. So that would be the angle at B13. So it's distance times the tangent of that angle is what's observed. And then subtract from that what they actually, oh, sorry, that's the predicted part. So that's the part you want to subtract from the other calculation, which is um, E9 times the tangent of, I'm not finding it here.
I got B9 times the tangent of the true position for the observer.
So that's one piece of it.
Okay.
And actually, I think that's the predicted. Well, no, it says that's observed. So from that, you want to subtract what angle they predicted for that, and
For the
that would
rise
be about
over or
for the rise minus drop overrun.
oh, got you. So GOP predicted
Yeah, that's
the
actually
217.
that looks too high. No, it's half of the distance angle less than that.
Oh,
Oh, actually,
the terrestrial drop.
you've got it as F16, but that's actually the same. So that's mixing up observed and predicted. So I think 210 is the actual predicted. So it would be minus E9 times F17. But the problem is over on B13, that's not really the observed, that's the predicted.
Yeah, we'll have to go over that later then.
Yep. Well, and I think that's true. I see a small difference, so see what that comes out to, I guess.
The distance times their occlusion angle came out to be 85,958 meters.
You need radians in there or
All right.
degrees. Let me see.
What do you do?
I just need to convert it to
Is
radians, and
it equal
then
degrees or whatever? I forget what it is.
I think inside the tan it needs to be the
All right.
tan is expecting radians.
Uh,
So
Why isn't it auto completing? There we go.
and I think that's radians is on there. It should be on the inside of the tan, not on the outside.
Inside of the tan. So in here, like this.
It needs to be around the B13.
Oh, gotcha. How many brackets can we get? All right, should be good. Nope. There we go. There we go.
That looks about right. Yep, that looks about
Eight
right.
55.
So,
Yeah. Oh yeah, yeah. When I did, yeah. That's so I have that down here. That's their true uh geometric peak based off of the
so, so,
conclusion at the
so you
star.
can use that value, I guess H19 is it, and subtract from H19 their equivalent predicted. And I don't see that already here anywhere. So what we're looking for is the difference between what was predicted and what was observed. That's the number we want, and that will be minus 30 when you get it right.
Hmm. Well, let's try H. Nine. Nope. Yeah, I don't know. We'll mess with it
Well,
later.
maybe it's this H. It might be this H10.
H10.
I think that might be their. Oh no, so that's their predicted for 217, but I don't see their predicted um for H equivalent of H F. Sorry, the equivalent of F17. Anyway, what's important is when you get the equations in there, they both have exactly the same error. It doesn't matter whether you're looking at from the observer location or from the peak. When you calculate out what the rise is in each respective case and subtract that from what was actually observed, so it's observed minus predicted. That or the way you've got predicted minus observed to give you minus 30. When you
Yeah.
do predicted minus observed for both, they will both be the same negative 30. And that's how I knew that we got all the rest of the numbers right. And that turns out to be true for every star, every peak. And every star is different for every peak. Every occlusion or emergence has its own unique number. That unique delta H, the difference between what was predicted and what was observed, is identical regardless of whether you're trying to calculate the flat Earth rise or the globe Earth
Oh,
rise.
yeah, Mike. So when I think that difference was being calculated by doing by comparing the what was it? Um by subtracting the prediction from like the flat earth angle, and that made it like circularly bind to the same offset. So like that's
So
why
the
yeah.
way I personally do it is I always subtract it from the globe Earth angle. I always make them perfect because we're trying to refute that
I know.
hypothesis.
No, I know, but that's why they're linked though, because we were subtracting it from the wrong thing. If you subtract it from the star true position, then it comes out to be 27 what it should be, and there's no difference.
So I disagree, and I think if you double check the math that I used, you'll find out that what I said was true. Um, and um, and the reason is all that math I put in the Death of the Globe Myth PDF last week. Um, that was actually explaining the math I was using. And then I sent you some preliminary math that's not quite ready yet um, for how to calculate the delta H. But when you calculate observed minus predicted for flat Earth, and you do that same thing, observed minus predicted for a globe without atmospheric compensation, you'll find that the height difference is identical for both.
Oh, okay, yeah, I'll have to go over that. I completely missed that. and now it's super relevant.
And
So yeah, I'll definitely come back to. I'll
yeah,
definitely
it
check that
becomes
out.
super relevant, and then you can use that to calculate a bunch of other things. Um, uh, because that's basically telling you the measurement error. Um, and once you know the measurement error, you can apply that to the 217 angle, when you call small delta, small delta, capital delta H, comma globe, comma peak. Um, so you can apply it to that one. You can apply it everywhere. It affects all observed angles equally. They're all off by that same delta. So that's the one that could be celestial refraction commingled with distance errors, commingled with altitude errors, commingled with uneven terrain. That just lumps all the errors together and tells you what the overall difference is that applies to every angle that's observed. So all observed angles are offed by that same delta H. And that's why that's very important.
Yeah, well, dang. Yeah, well, we will definitely be going over that next week then. In between now and then, I will get on top of that. Yeah, I thought it was a circular mistake in what I was doing. So, because when I
Yep, and I'm
changed it
sorry for any
to that,
confusion.
no, yeah, no worries. Cool beans. All right. If are there any questions, comments, or concerns, lads and ladettes?
I wonder if I could just take a couple minutes. You misrepresented the globe method a couple of times. I just need 2 minutes to correct the record.
Sure, Sean, go ahead.
Okay. So the globe method is pretty simple. We say that the visual occlusion happens when we see it happen. That is, when the visual elevation of the star is the same as the visual elevation of the peak. So to be specific, in the case of Mike Heffron's observations of 39 Aquarii and other stars at Pikes Peak, we would, if we wanted to predict the time, we would say, first of all, we'd calculate the visual elevation of Pikes Peak from Heffron's Place. That's 2 degrees, 19 arc minutes. After you subtract the 200 meters of globe drop. And then we would simply look at the star in Stellarium and just ask, when is that star going to be seen at 2 degrees, 19 arc minutes? That's the method. That's it. And you can do it that way to predict a time, or you can simply look for when the occlusion happens and then look up what the elevation was. Either way, it'll be 2 degrees, 19 arc minutes, not 2 degrees and 33 arc minutes, which is what you get with the flat Earth method. And that globe method, it's that simple. That's it. Don't need an hour to present it. That's it. It works within 2 or 3 seconds for every peak. Thanks.
Nice.
If I could respond to that, Alan,
Absolutely.
Every week John jumps in and he says we misrepresented the globe method, and
Real quick before you do that, remember last week when I went over his position accurate, like, same thing. Like, he just reiterated what we just said, but he prefaced it with that we misrepresented the globe, but like we didn't, and we went over it last week identically, and he was like, dude, great job representing it, you totally get it, but nothing I said in this presentation misrepresented the globe at all.
Well, okay. So I'm sorry.
Anyway,
last week
one second.
You did something else. Last week you did correctly steelman my diagram, which I'll put up again. Didn't find anything wrong with it. It does indeed give all of the angles correctly and coherently, and that's the good thing about it, right? I'll put it up again here. There it is. I just put it in the chat. It's a simple diagram. You can, it does take looking at it, but it correctly gets the geometric directions, the visual directions. It gets everything right. But that's different from the method, right? This week I was correcting. You were talking about the globe method, and you misrepresented the globe method.
No, absolutely didn't. This week we're going over the geometric implications, right? Last week when we were covering your apparent position stuff, that's what we were talking about. This week, we're going over the geometric implications of the globe, and you felt the need to step in and say that that's a misrepresentation because when you bind the globe geometrically to what it predicts, it doesn't actually work out. So anyway, Mike, you were about to respond.
Right, and my response was going to be, I think John tries to do this every week. He tries to make this, oh, you misrepresented. But what John has consistently failed to recognize week after week after week after week is this is not about the globe method. This is about refuting a null hypothesis, where the null hypothesis is the exact opposite of the globe hypothesis. The globe hypothesis states that the Earth is a globe. The null hypothesis states that the Earth is not a globe, which we interpret to mean the Earth is flat. And so the point of the whole experiment is to prove that wrong. And that in that way we would validate the globe hypothesis. But in trying to prove that wrong, what we have found consistently over and over and over again is we cannot prove that wrong because the angles on the peak are the flat Earth angles. And what we've recently discovered, the delta H is why there's any inconsistency at all, but that inconsistency is shared by the globe angle reported by Stellarium and the flat Earth angles reported by Stellarium. And contrary to how some people want to confuse things, um, Stellarium is consistent with both a flat Earth and a globe Earth. It's representing things as angles. And the distance angle, what I call the distance angle, is particularly important, which is 360 times the distance over 2 pi r. All that is distance turned into an angle so that you can subtract it to see what the angle should have been. And in all cases, those agree with what Stellarium's reporting. And I think our globe Earth friends are not following along and they're not paying attention to these numbers, and they want to keep insisting they're right without looking at what we've done.
Dude, that's
Um,
that's 100% true because we went over it explicitly last week, the refraction position, and also if you derive the distances and elevations based off of the refracted position, it doesn't work out per following our methodology. So none of what was stated was applicable. But again, like real quick, the big significant part of this is why we went over the 360 thing so much here, because when this star traverses this 27 seconds of arc in the sky relative to that distance on the ground, it's getting intersected and it's no longer visible when it's within 2 arc minutes of this peak, rather than for the globe predicting that it already intersected with the peak and is now at 2 degrees 6 arc minutes below it. Like the position is untenable, yet we got to grant it to them and let them do their thing or whatever. But the arc was intercepted at this angle, not this angle. This is the significance, right? You can go into Stellarium and do that all you want, and if it magically works out, that's not going to tell you anything. Or I say magically, but if it's like within a couple arc minutes of what it predicts, that's not going to tell you the true cause of the occlusion. We're interested in the cause. That's why we invoke the geometric positions for the analysis, because that is what did the occluding at that actual intersection point. So if the arc of the sky isn't intercepted at the relative elevation angle for the drop over distance to lower that peak, then the Earth's not a globe. That's very simple to understand.
You made a comment then about the geometric position during occlusion. Where is the star? What is the geometric position of the star?
It's an angle off of the horizon.
No, but where is it? Right? You need a geometric position to draw a geometric diagram, right? The star must have a geometric location for that angle to exist.
would it be okay for me to answer Dosma's question? Because I
Certainly.
understand what he's asking. From the globe Earth perspective, the geometric position is at C13 is 2 degrees 6 arc minutes. from the flat Earth positions is G3, which is 2 degrees 31 arc minutes.
Not quite. I mean, physically, where is the star? In your model, how far away is it?
Dude, what does that even mean?
Because my understanding
Completely
is, like, if you have
irrelevant.
a geometric model of the flat Earth, you can draw everything in its place, measure all the angles, and one geometric model will work for everything. But you need to draw a geometric model for every individual scenario, and no two geometric models line up with each other.
Our position isn't that multiple people can triangulate the same star. Moving it out to infinity doesn't, like, we don't care. You have a gross misunderstanding of what we care about in terms of a model. All we care about? No, it doesn't. All we care about is finding distances on the ground using positions of stars that intersect and when they're intersecting. Making a conceptual model to which you could say, hey, everyone over this distance, if you move the star out to infinity based on XYZ factors, is irrelevant. If you're going to use celestial navigation, you can use the same altitude. Goose has it modeled out. I'll get you a link to it. But he used the exosphere distance, which is like 6,200 something miles. And then it's like it exponentially goes out from there to like infinity or whatever. But like the baseline for what it starts at is like 6210 something ish. And that works just the same. It doesn't matter where they're actually at in terms of like distance away from us. That's a conceptual model. We don't care.
Yeah, but everybody needs their own exosphere in that case, don't they? There's no single geometric model that works for everybody simultaneously.
If I could jump in again, I agree with Alan. What you're saying is totally irrelevant. This null hypothesis is all based on 2D angles, and those are the only two angles that matter.
The null hypothesis doesn't refute all of the cases, though. We can show a large number of cases where the null hypothesis will fail, right?
Bring it.
Which ones specifically?
Let's see it.
So, or the very worst case, it can't distinguish. So all those high elevation angles, very short elevation or short distances where you cannot distinguish from the globe, that's evidence. I just pasted one in. It's a hypothetical, but it's one that I can go and reproduce, where you've got a negative angle. And that's why I asked where the star is. If the angle to the star is negative at the time of occlusion, what is going on there?
Bro, we went over this last week. The mountain it creates an artificial stop. I don't care if it's to your satisfaction, dog. It's the answer that what it is. You can't just come here and be like, hey, I'm going to ask the same thing again, even though the answer is that it's an illusion based on the fact that the other mountain peak creates an artificial horizon. You're not on the ground. You're also on a mountain. There's more sky behind the mountain peak. That's the answer. It's not geometrically below you at an actual negative angle, man. That's it. Like, if you don't like that, don't accept that. That's fantastic, bro. I don't know what to tell you from there.
Why does it apply when it's geometrically above? If it doesn't apply when it's geometrically below, you said the geometry.
It's always above. You would only say it goes below when it's out of your field of vision. If you were out on a ship, they have what's called the boundary layer. It's like half a degree above the horizon. Nothing sets into the fucking ground, man, and goes negative like that. So when it's just not visible, we're just saying you can't see it anymore. It's out of your vision. You're saying it's beneath you. I don't care. It's never below you. If it was ever being indicated that it was going below you, bro, guess what? The angle that the arc of the sky that it's traversing over that distance would get intercepted at a lower angle because the peak would also be physically lower. But that never happens. So it's not actually going below you. That's it. Simple as that. If that's not to your satisfaction, then your satisfaction can't be met by me. Sorry.
So the angle is negative, right? This is definitely a thing that happens. You can get negative angles.
And if you did a dip correction for the same thing, like what you would do normally, it wouldn't be negative, bro. That's because listen, dog, stop. The fact that the dip correction is the thing that fixes it, it's non-physical. That's it. That's all you need to know. That's all I care about. It's not something.
Nothing to do with this. Right?
All right. Got it. So when you're above sea level, the dip correction has nothing to do with fixing it. Got it.
Yeah, so because we and I pasted an image. This is the scenario that I can reproduce locally, right?
Mike's already done it, bro. Mike did it.
So we have
we've literally had this exact conversation, and Mike's been over it and presented you with the data.
a negative angle.
Can you hear me? Is this hello?
Greenhorn Mountain.
No, it wasn't green. It was cotton something.
Oh,
it was cotton something.
Cottonwood Pass.
Cottonwood Pass. We've literally been over this exact scenario. It's fine, man.
That's totally irrelevant to this.
So Cottonwood Pass that gave you a negative angle, did it?
Yes, and the globe negative angle wasn't met. They predicted a much greater negative angle. It means nothing.
That's fine. What is the geometry of the negative angle? Where is the star?
Instead of arguing, this is all nonsense, Daza. Greenhorn Mountain and North Peak both have a negative angle. The uncorrected globe Earth angle from the observer's location is negative. That peak is 130 kilometers away. It should not even be visible from my house, and yet you can see it clearly occluding stars. So stop with this negative angle nonsense and your interpretation versus flat Earth interpretation. The flat Earth interpretation is what you don't seem to understand and what you cannot refute, no matter how much you try to bring up this negative angle nonsense.
Well, I can refute it because I have other geometric measurements of these kind of things that show that the angle is truly negative.
You're not refuting anything. What we are calculating is distance times the angle. We don't care whether that angle is positive or negative.
But your geometry makes no sense if the angle is negative. It will put the
it doesn't make sense to you because you're looking at it only from your perspective, and you're not looking at it from the perspective of trying to refute the null hypothesis. The null hypothesis does not agree with your perception, and you are unable to refute the null hypothesis.
I am, because I have other geometric measurements that are available. Even for your locations, we have geometric measurements that are available that refute your conclusion.
You say this refutes it, but you're refuting it based on your correction factors. You're not refuting the null hypothesis. The null hypothesis says what that angle will be, and we can demonstrate that's what the angle is.
We have non-optical measurements of the geometry of those peaks. We know where they are. They do line up with the traditional optical ones, but we know the elevation of those peaks through non-optical methods.
No one's disputing the physical elevation of the mountain. We're using it in our rise over run to derive the angle of interception as the star does its central angle across the sky and should be intercepted at one of two angles: the rise over run to the peak, or the rise over run minus the half of the central angle as drop over distance to create what the globe would predict for the physical angle. Turns out it doesn't get intercepted at the globe angle. That's it.
So the globe can, and this is what John's argument is, I believe, that the
real quick, John Daza, Daza, can you hear me? Listen, real quick. You said you had measurements and data. Start linking the videos of the occlusions and the data so we can see how the flat Earth prediction was not met and how the globe Earth prediction superseded us. If you don't start linking that stuff immediately, I don't care about anything you're saying. If you have, like you said, you had some data to show, start linking that right now. If you have occlusions that with negative angles, start linking it now. I'm unmuting you. Go ahead.
Yeah, I'm going to measure the negative angles, but the data that you're using for elevation is geometrically independent of your measurements, right? Your elevation data is geometric data.
Real quick, Daza, specific instructions were given. You said you have some data to refute what's being put forward. Last week, when I asked you for the transformations with the z-axis thing, not alignment, you said, I have Stellarium source code open, as if you were going to start linking it. You never linked it. I have no idea what you're talking about. Link the thing that refutes what we're doing now so we can compare. Yeah, if your sentence isn't presenting the data that you were just talking about, it's not relevant. We've heard all the sentences. Now we need the data to refute your sentences. No more sentences need said. We need triangles now. All right. Does anyone else have any questions?
I have a comment if that's okay.
Go ahead.
Um, I just checked the spreadsheet, uh, and when I calculate delta H, I am taking the observed angle minus the predicted angle. And when you do that, you come up with the same delta H for the peak as you do from the observer's location. And that's very significant because it means we're all dealing with a common error, um, uh, which is the difference between the observation and the um, prediction. It's the same error in meters for each peak, each star, regardless of whether that's observed from the peak or from the observer's location.
All right. So you said subtract the true pause from the other true pause?
Yeah, and on this one, there's an error on that one. Or sorry, on
Actually,
this one, I don't know.
I'll go to Pikes Peak. I'll go to familiar territory. That's my baseline
on that
for
one,
calculating everything.
that one had an error because C13 and G17 are essentially the same. They're like just fraction of a arc second apart. And I think the real number is the deviation is something like 3. I might be able to look that up quickly.
Oh yeah, I already have that down here for the arc comparison. Yeah, I don't know.
Okay,
We'll go.
it looks like the real deviation is something like 2 arc minutes, 45 arc seconds, something in that neighborhood. It's a really tiny error, but it's significant.
Yeah. All right. Well, with that, we will wrap up for the night, lads. Appreciate everyone hanging in there. If you have any questions, comments, please feel free to question, comment, and if you want to try and refute it, please, provide the actual data. Don't try and just like shoot it from the hip or whatever. That's not gonna cut it. We've been at this for 20 weeks now, and we're trying to make this as accessible and understandable as possible. But we can only, I don't, however I can do it better. Feel free to tell me. Just leave me a comment or whatever. Tag me. All criticism is welcome. I am here to help. All right, that concludes our Celestial Theody session. I'm going to wrap up the stream now. I'll be back in a sec. All right, let's see what the lads are doing in the chat here. What do we got going on? Bring the boys out here. We got Earth first, space later, Shalom, PJ, Tony Coriolis in the house, Bretimus, shout out to your boy, Flat Earth Daily, Flat Earth Eric. Wait, Flat Earth Eric Daily. Okay. That's the first time I've ever read it. I just made a bunch of assumptions that Eric was in between there, and then I started to question myself, and I was like, "Is his name Earthrick?" Earthrick. Anyway, problem was me. All right, calm down. See you out there, Big Pine Sailing. Shout out to the boys. We'll see you guys next week. Much appreciated, everyone, for coming out. We'll see you guys at the Big Triangle Festival.